I think we are, let me just try something fast. Okay. Just making sure. Yeah, okay, so anyway, we went through the whole introductory stuff, and if you came in late, there's a handout on the chair over there. And we're going to go straight to well, we're going to be talking about force vectors today in 2 dimensions. And tomorrow we'll look at 3 dimensions, and we're going to be talking about a particular representation of force vectors, which is the Cartesian notation. We'll talk a little bit about the the laws of trig, but that we can kind of skip a lot of that stuff because it's just kind of too distracting. Anyway, not that you have done the reading, but you probably should know this anyway. Which of the following is considered a scalar quantity? Mass, right? Because everything else is directional, right? Forces, positions, and velocities. You might not have thought about that too much, but positions also are directional. We talk about them relative to some reference point, and so there's a vector orientation associated with that. And if you want to add vectors, you're going to have to use, what are you going to have to add? Which law? Newton's second law? Nope. D, the parallelogram law. It's not a physics problem, it's a math problem, adding vectors. And the parallelogram law says you can add vectors by drawing a parallelogram with the 2 vectors at the corner, and then extending that out. And at the end, the far corner of the parallelogram is where they will go when you add them together. I will explain that in today's lecture. So the application, very practical, is suppose you have some bracket with like 4 wires attached to it, and you want to know like what is the net force maybe acting on the anchor, that point here where the, oops, I still haven't calibrated my cursor. Maybe I should stop and do that. Well, hopefully we can get by today without that. It might be a little bit messy, but anyway, yeah, so if you want to know what is the net force on that rock or whatever that thing is anchored into, you would want to maybe add up all those forces together. But you don't just add the magnitudes because they're off at different angles. So you have to sort of add them in a vector sense, because the actual addition of the vectors will probably have a smaller magnitude than the sum of all the magnitudes of the vectors separately. If that makes sense, right? So we want to have an accurate way of doing that, and that's why we have to learn these vector approaches to adding force vectors and other things. So the differences, of course, between scalars and vectors. Scalars are just quantities without any sort of direction, like mass and volume, and vectors are they have sort of a size and a direction associated with it. So in this presentation, you will actually, and in future presentations, I think I went and changed them all, you'll see vectors represented in bold, red, italic. So that's how you can tell if something some symbol that you're looking at on the presentations is a vector or not. And magnitudes will generally be, I think, just black and not italicized. But when you're trying to add scalars, it's pretty easy. You just add the quantities together, and there's no special notation. For vectors, though, you need to use something like the parallelogram law or the triangle law to add the vectors tip to tail. And then, you might also have other notations like an arrow or a caret on top of them. So mathematically speaking, if you have a vector of some size A, you might think of scaling that by multiplying it by 2. You can scale that vector, and you have something now called of size 2a. It's twice as long, but it's pointing in the same direction. You could actually scale it by a negative number, in which case you'd be flipping the direction, so it's pointing 180 degrees opposite of the original direction. And 1.5 means it's going to have a larger size, but it's also pointing in the opposite direction. You could also reduce it in size. You could scale it by a half, and now you have something that's 0.5 times the original vector. So these are all different ways of just sort of multiplying or dividing a vector by a scalar. So whole number. Now, but what if you want to add two vectors together? And this is where the the parallelogram law comes in. And the parallelogram law says, suppose you have vectors A and B and you want to add them together. What you're going to have to do is, you could create a geometric parallelogram where you put the the tails of both of those arrows, you join them together, and you can sort of sketch out the parallelogram that forms with those as the sides. And then the resultant of those two vectors R is the one that goes from where the two tails meet to where the opposite diagonal of that parallelogram ends up over here. So this is the resultant. Changes to red, so it stands out a little bit. And let's see if I click on that. That stays red. So this is the sum. This line here is the sum of those two vectors, and we're just saying, it's like, well, if someone gives you some directions, walk east for, a half a mile, and then go south for a quarter of a mile. You can imagine visually you're sort of going, east for a half a mile and south for a quarter of a mile. You can think about, the total distance as the crow flies, so to speak, right, as being the hypotenuse of that triangle. And but again, you can think of that as the parallelogram law, just building that parallelogram. In this case, it's a square because those directions are orthogonal to each other. But you can sort of think of that's sort of what we're doing here. If you're traveling down vector A for a certain distance, and then you're going to turn and travel down vector B after that for a certain distance, you're going to go, this way so far and this way so far. And when you finish, you're going to be ending up at the tip of that resultant vector. The triangle method just says, well, forget about the other side. We just really want to add vectors by, you can start here at this point, go a certain distance in A, and then just bring in vector B to continue on in the B direction, and then you end up at this resultant place here, R, which is A plus B. And it doesn't matter which track you go on. You could start going down the vector B path if you want to, and then go down the vector A path, and you'll end up at the same place. So geometrically, that's all we're sort of doing with vectors. So what if you want to subtract a vector? Or subtract two vectors? Like what if you want to do A minus B? How would that look? What kind of triangle would I draw if I was going to try to do A minus B? Sorry? The arrows pointing together, that's an interesting idea. Let's see. Yeah, since we, well, I mean, those are both kind of valid. If you do want to do A, what I was sort of getting at is A plus negative B. If you get how, you can invert the direction of a vector by multiplying it by -1, right, then, yeah, you can talk about A plus negative B. If you form negative B, then you've got a vector that's kind of going this way, right? Right? And in this case, you can do the triangle or the parallelogram law and then go from here to here, right? And this becomes, A minus B. You can sort of get that if you put them tip to tip. I think you had kind of a good point there. If you kind of went like this, you kind of have a triangle that kind of goes that way. But it's a little bit confusing about which way you're going, but you can kind of see that same triangle that way if you're doing tip to tip. What if you want to add more than two concurrent vectors graphically? What if you want to add like like in the original problem, there's 4 vectors. What if you want to add 4 vectors together? How are you going to do that? Head to tail, a whole sequence of vectors, right? Head to butt is usually not considered a proper way to talk about vectors. So if you had 3 vectors coming out of a bracket, you could start on the the A path and then go on the B path and then go up the C path, right, like that, and string them together, and oops, and then this is your resultant there. Sorry about the mess there. Okay, so those are all different ways of handling vectors. Yeah.
Adding vectors, can you start with
yeah, it doesn't matter which one you start with, you'll always end up at the same place, as long as you have those 3 in the sequence. Yeah, that's the interesting thing about vectors. So now we're going to kind of go closer to a real, I mean, that is geometrically what's happening, and it's good to be aware of that. And that earlier trig stuff, which I threw out, kind of emphasized that thing, which is, it's useful, but people kind of got lost in the trig and say, why bother? Because you don't really need to worry about all that trig. If you think about resolving a vector into components, in other words, suppose you have a vector and you want to express it in terms of 2 other vectors that are oriented in some arbitrary direction. They don't have to be 90 degrees apart. Like this B direction, this lowercase b direction, or this lowercase a direction, are considered vectors. And you could think about, well, how could we represent this r vector in terms of the b and the a directions? And you can see that it's pretty easy to imagine a parallelogram. Again, you would have to say take the tip of your r vector, which is right here, and extend, towards the b-axis by traveling in the a direction, or the minus a direction, right? So kind of going there to build that parallelogram. And that will give you the size of b that you would need, right? And then you could sort of travel towards the a-axis along the b direction, which is perfectly horizontal, right, until you hit the a-axis, and then that intersection point is going to give you how much a you need, right? And you just basically form that parallelogram starting with the diagonal instead of vice versa, right? And those components A and B then are said to be the resolution of R along those little a and little b axes. Okay, and so that's the point that leads us to the Cartesian representation, because we have this nice, nifty Cartesian system with perfectly orthogonal axes, which makes it really convenient for a lot of our representation of geometrical things. So let's use that and represent our vectors in terms of Cartesian components that align along the x and the y axis, right? So you can take this force vector f and represent it in terms of an fx, which is going along the x direction, which is indicated by this unit vector I. And then you have an fy, which is going along the y direction, which is indicated by this unit direction j. And so I cleaned out the slides, but not the stuff. So still a little bit of a mess there, but I'm improving. I'm looking at my notes online. So we've resolved those into the x and the y axis, and each component is shown as a magnitude in a direction. Notice the components are actually just given in regular face. They're not bolded, right? These are just magnitudes of the component in the j or I direction. And we use unit vectors I and j to designate the x and y axes. So, for example, if you have this vector f, you can write it as fxi plus fyj. This is probably not new to you, right? Because you're either in or have taken 20C, right? So what I'm saying, I guess, is sort of kind of like review, right? is not really terribly exciting yet. You also don't have to, well, I guess this is just a different vector, f prime. And you can see what's interesting about this one. I think they're trying to make a point here about the sign of these things. Notice that the fy component is going in the minus j direction, right? And I think that would sort of imply here that f prime y really should be listed as negative, but it gets a little confusing until you look at a real situation. So, but the other point is you don't have to, your x and y axes don't really have to be oriented horizontally and vertically, as long as you're free to sort of tip them to match the orientation of the problem that you're solving. If you're looking at something that's on a slanted surface, it might be easier to slant your whole x and y system. Like we sometimes do when we actually work with friction. If you have a box here, it might be more convenient to think about the y-axis going this way and the x-axis going that way, right? So those are you're free to tilt those things, is all they're saying. So rather than, this is one of the advantages of the Cartesian system as opposed to that more geometric trig-based one where you have to you're trying to add like 4 vectors, you've got to do this lengthy, sketch of one vector attached to the next vector, attached to the next vector, and so on. The easier way is to resolve each force into its Cartesian components, right? And then just add up those components together to find the resultant. Add all the x components, add all the y components together, and then voila, you've got your resultant. That's the kind of a quick way to do things. So you add up all of them together, and then your resultant in that case will just kind of come out of that. And then generally when we're finished, we want to find the magnitude of that resultant and then what direction that is relative to the x or y axes. So we'll be trying that out in the example problems. And then here is a particular kind of sort of fleshing out that in case you want to sort of see that in detail. We have to sort of go through the step of, for each vector, we have to sort of expand it into its components. So this is f1x, and then f1y, and f2x, and then you have f1x and f1y, and then f2 is being expanded here, right? And f3 is being expanded here, right? And then you can essentially group all the terms together. So you have f1x, f2x, f3x, and f1y, f2y, f3y. You lump all those things, add them together, and then your resultant has an x and a y component, which is determined by those 3 other subcomponents. You notice something interesting. Why is there a minus sign in front of f2x? Yeah. So you might find as you're doing this, you might be given an angle or something like this, right? And maybe this is a magnitude, and you kind of know the base there is going to be 10 times the cosine of 30. Hopefully you're good with that, and then you know that it has to be negative because it's pointing in the negative x direction, right? So you got to stick a minus sign in front of there. And sometimes you can just keep this thing positive and just put the minus sign there if you're talking about a variable. Anyway, one of those things about that people can kind of mess up. It's easy to make a sign error in these kind of problems, so it's really helpful to just constantly refer back to the problem statement, look at the geometry, and make sure when you write your components, if it has a, if it's sort of going in the minus x direction, that there should be a negative sign in there somewhere, right? If you forget that, then you're going to be doing something that's, not correct. There was someone said they were looking at Cal Poly's class or something they found on the internet, and they at the end of each problem they had to actually write a statement on whether the answer made sense, given the geometry of the problem, right? Like for instance, on this question here, if you look at this problem, what would a correct answer sort of be? Do you think the resultant should have a positive x component? Just looking at the geometry, right? Not even any numbers involved. Do you think the final answer should have a positive x component or a negative x component? Should be kind of positive, right? It looks like there's more stuff when you have the x component of F1 and the x component of F3. They seem to be outbalancing the x component of F2, which is going in the opposite direction, right? So the answer should have a positive x component, right? And what about the y component? Should it be positive or negative? It's probably a positive y component, right? So the resultant should be somewhere in quadrant 1, right? So if you get an answer that's in another quadrant, then you can catch that early, right? And you can go back and find the mistake and fix it. So it's kind of a good skill. I don't, you know, at this part of the class, you're more going to be concerned about the mechanics of doing these things. But taking a step back and looking at, does this make sense from a higher level? You know, it's a really good skill to have, to just kind of take a step back after you finish a problem and just sort of assess it. You can also represent, so the other thing is to get the magnitude and the angle of a vector. So if you have this vector where you've got a resultant and you want to break that up into, well, you have the components, frx and fry. What is the magnitude of the resultant? Well, according to the Pythagorean theorem, right, this is a right triangle because it is a Cartesian representation. And that means this is the hypotenuse of a triangle that has a base of frx and a height of fry. And that's the square root. Pythagorean theorem is square root of the square of those things added together. And then this is the triangular, you know, trig thing of the definition of the tangent, that the tangent is going to be fry, right? The tangent of theta is fry over frx. And so the angle is going to be arctangent of the ratio of those guys in degrees, right? So, all right, so let's tackle an example and see how this goes. So we have three concurrent forces acting on a bracket, and we want to know what is the magnitude and angle of the resultant force. So we're going to resolve the forces into the x and y components, add the respective components, and find the magnitude and angle from the resultant. Okay. So that's the plan, right? And actually the other thing is you might want to just sort of sketch this plan on here. I don't know if it's not on your handout, but that is the master plan. That's the course that we're going to follow in tackling this problem. And again, you know, having that master plan in your head is again, it's your high level, you know, sense of where you're navigating through this problem, right? And it's good to always have that in your head as well, so you don't get lost in the path. You know, you want to keep track of what your goal is. So we're given these things, and we're asked to find the magnitude and the angle. And our plan, which you can think through before you do any work, is going to be to resolve those forces, add the components together, and then find the magnitude and angle from the resulting components. That's our plan. So now we're going to start tackling this problem step by step by representing the three forces as Cartesian vectors. So F1 is going to be, we're going to sort of write that out. So F1, now you notice actually, and they have, the way they've got the angles specified is different for each one of these things. F1 is, the angle 40 degrees is relative to the y-axis, right? And just, you know, I did skip over the trig part, but let's just let's kind of just list some of these relations here, because I think my impression is that people are a little bit sketchy on trig when they start this class, and I want to make sure that we get some of these things clarified. The reason I think people are still sketchy on trig in this class is that I still see people, like on the test, they're actually kind of writing that, what's that acronym, SOHCAHTOA or something, where that sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is the opposite over adjacent, right? And that tells me that they haven't really internalized it yet, or people are still a little bit, unfamiliar with these things. Once when you go in an engineering path, this is going to be something you just do all the time. So eventually you won't need that. But just as a refresher, right? So what that means is that the sine, so sine of theta equals x over h, right? And that means if you're interested in x and you have h and theta, that means x equals h times the sine of theta, right? Cosine of theta equals, oops, I messed that up, didn't I? Nobody stopped me. Luckily, my internal navigator said, well, the sine is opposite over hypotenuse, right? So it's y over h, and y equals h times the sine of theta. And cosine of theta equals x over h. Implies that x equals h times the cosine of theta, right? And then the tangent of theta equals y over x, and that means you could say that y equals, whatever, that doesn't really matter, but x times the tangent of theta. Tangent is a kind of a special, normally we're using, oops, or you could say that theta equals, actually let's do it this way, let's see, that sort of means that theta is the, the arctangent of y over x. Okay, that's all the trig you really need to know for this part of the class. It's really, really basically simple. So what is the x component, knowing that, what is the x component of F1? Yeah, 15 cosine of 50. Yeah, that's true, and you can add the missing angle there because it's the, if you want the x component, that's got to be, if you're going to use cosine, it's going to be the adjacent. Or you might also have written this as what? Yeah, because they gave you that angle 40, and if you want to know this horizontal distance, that is considered the opposite of the angle 40 degrees, right? So you got to use the sine for that, right? So they do those little things just kind of throw you to make sure you're paying attention. So you could have said or 15 sine of 40. Okay, and that's going to be, in the I direction, and what is now the y component of F1? Well, 15 times the sine of 50, right? And that's basically F1. You can put an arrow on top of it. What about F2? What's the x component of F2? Well, F2, interestingly enough, has this weird, what's the angle here, right? 5, 12, 13. What is that? Is that a 30, 60, 90 triangle? No, it's a 5, 12, 13 triangle. And the angle, you could find theta as the, say, the arctangent of 5, 12, right? If you want to do that, but you don't have to because they're giving you a similar triangle, right? So what is the, let's think about it. You could say it's, let's see if I blow this thing up here. 5, 12, 13. If you're thinking about this as theta, then theta, what is the cosine of theta? $12 over 13, right? It's the adjacent over the hypotenuse, right? And since, in general, we don't really care what theta is, we just need to know what the sine and the cosine is, you can just use those numbers when it comes time to take the cosine or the sine. See what I'm saying? So whenever you get one of those triangles, they'll give you a 3, 4, 5. They'll give you a 5, 12, 13. I think that's the only ones I normally see. So in this case, we're going to have the x component is going to be 26 times the cosine of theta, which is 12 over 13, right? And then the y component is going to be 26 times, what's the sine of theta? Yeah, 5 over 13, right? Times j. Okay, does that look right? Do a high-level check here. Does that seem like it matches the problem statement? It shouldn't it be negative? Yeah, right. So already, you got to start worrying about that quadrant, right? Because this vector's pointing in the left direction, so we got to put a minus sign in front of it, right? Yep. And F3 is 36 times the cosine of 30 degrees, right, in the I direction. And this time I know, okay, it's going in the negative y direction, so I'll put minus 36 times the sine of 30 in the j. And that's the three forces. And so the resultant, which if you kind of crank all that through, so you're going to essentially, add all those together, and maybe I can draw that with another color here. I take these three, and I add them together, and this gives me, it should give me the number 16.82. And if I add all of these guys together, that should give me the number 3.49. And this is J, and this is I, and it's plus. So our resultant, which is the sum of those components, is going to be this plus, it's plus that. I don't really want a dot there. Something like that. So that is our resultant, just kind of doing all the arithmetic in there. And common sense, does it pass the common sense check? Yeah, because it seems like there's definitely a pretty strong pull to the right, and it seems like there's more pull up, although it's getting close to zero there. So but anyway, it seems reasonable. So that is our FR, and the magnitude FR, which is FR without a arrow, is going to be the square root of the sum of squares of those things, 16.82 squared plus 3.49 squared, which will give you 17.2 kilonewtons. And the angle is going to be the arctangent of 3.49 over 16.82, which is going to give you 11.7 degrees. And so you could sketch this thing out. So you're going to have something that's going to be a magnitude of 17.2 and an angle of 11.7 degrees. That is your resultant. Okay, questions? guess I was supposed to do this on the next slide. Well, anyway, this is the answer that you'll find in our PDFs. And we occasionally have these little concept quizzes. Can you resolve a 2D vector along two directions which are not at 90 degrees to each other? A, B, or C? Unique being there's only one possible way, or not unique being there's a million possible ways.
That's what we've been doing, right? This entire session is having vectors that aren't 90 degrees.
Yeah, that's true. But this is talking about resolving, not adding. So resolving means, and let's explain what that problem is. So it kind of helps. So what does resolving mean? So resolving means if you have some vector and you want to resolve it in terms of two other vectors that are at 90, that are not necessarily at 90 degrees to each other. So let's sketch that out. This goes back to the basis of the Cartesian thing, right? So suppose we have two directions. One maybe going this direction. We'll call this the B direction. And maybe one going in this direction. We'll call this the A direction. They're purposely not 90 degrees. And the question is, if you tried to break up R so that it was written in terms of the sum of a vector going in the A direction plus a vector going in the B direction, first of all, can you do that? Because answer B says, no, you can't do that at all. Or if you can do it, is there only one way to do it, or are there like a million ways to do it? First of all, do you think you can do it? Does it seem like something you can do? Yes, okay. Amir says yes. And then the question is it unique or not unique? Can you imagine like a lot of ways of doing it, or is there only one way to do it?
We tend to be able to do it a lot of ways.
Try to visualize it, okay? You're trying to get to point R, and the roads are only going to allow you to travel in the A direction or the B direction. Now the distance, and really we're talking about those vectors, right? Okay, because the parallelogram you could either travel down A first, you could travel down B first, but that's not our question. The question is the magnitude of how far you're going to travel in the A direction and how far you're going to travel in the B direction. Is there only one answer to that, or is there more than one answer? Can you visualize it? Can you just mentally make that visual traveling around? What do you think? Someone just throw out a guess. How many people think it's unique? How many people think it's lots of ways? About 50-50. All right. So I will show you one way to do it, and then you people who thought it was not unique can try to figure out another way, right? So the parallelogram law says you can do it with a parallelogram, right? So we have to start at the tip of R and move towards the A axis, but only by traveling in the B direction, right? You see that? And that tells us that the size of our A vector is this. And the size of our B vector is this. And that means, you got to go, this is our A vector, and this is our B vector. A little messy, right? Now, what other way can we go in those A and B directions? Of course, yeah, the other side of the parallelogram, but that's not a different solution, right? That's still, the A and B are still the same size. You're just putting them in a different order. So who can tell me another way to do that? I can only travel down the A and B directions. What other way can I do that? To come up with different sizes of A and B, right, and still end up at R. Can anyone see one? Chris? Can you use the X and Y vectors from A and B, like break those into X and Y components and work from there? But that's sort of using different directions, right? So the answer is no. There's only one way to break it up. It's unique. Now the next question says, what if you try to resolve a 2D vector along 3 directions? Would that be unique? And it's kind of fun to think about these conceptual things, right? So I imagine you could do it because the third vector you could always just put to 0. So now suppose you're trying to get from, 0 to R, and you have three different vectors, maybe 3 different directions. Maybe you have like one going this way, one going that way, and one going maybe 0, 60, and 120. They're saying. Right? Suppose we had 0. Let's do one at 0. Let's just do the 0 one, maybe going this way. 60, which is kind of like going that way, sort of, and then 120, which is kind of going this way. I may be belaboring this, right? But can you see, in this case, you would have multiple ways of going there, right? Like you could travel a certain distance. You could travel a certain distance in the first vector direction, right? And then you could travel maybe all the way up here in vector 2. Oops, I think I went too far. So maybe I could go back in the vector 3 direction in the opposite going there, right? And then maybe, I could go up this way, following that vector, and then kind of going there finally to get there, right? So there's a lot of ways. That's one way, right? Or I could start off by going maybe this way, a certain distance, and then maybe traveling up here. You see how I'm kind of restricting myself to those 3 different directions? And this may be very confusing to you, hopefully not. I could travel horizontally for a while. I could go past R, and then come back down with this direction here like that, right? So there's multiple ways of getting to R. Anyway, maybe that's not so interesting. Any questions on that? But hopefully that you can kind of see there is only one unique way to resolve a vector when you only have, in 2 dimensions, you only have 2 directions to travel in. But when you have 3 vectors, then you can have multiple ways. I think your sheet has another problem on the back, right? And this is basically the same kind of problem. These things are just the fun of it. You've been doing a lot of these in this week's homework. And here we have a similar situation with 3 forces acting on a bracket. We want to find the magnitude and angle of the resultant force. And again, our plan is going to be we're going to resolve each force into those components, add the respective components to get the resultant vector, and then magnitude and angle from the resultant components. Does everybody get the difference between resolving and resultant? That's actually, I think, for beginners, that's sort of sometimes. Yeah. Resolving is like breaking it apart, a vector apart into multiple components. And the resultant is like putting them back together into one, right? So they're like opposite processes that you're doing. Resolving is breaking apart. Resultant is bringing together, right? And so we're shattering these vectors into their components in the horizontal and vertical axis so that we can add those together and find the one resultant. Okay, so, and we can just sort of, it's always good practice. The resolving part is sort of the, I think, the challenge just initially. So we can start with the F1, the F1 vector, resolving the F1. What are the components of F1 going to be? I can call on people that I happen to know at this point. Emran, what would be the F1 component, the X component of F1? Don't do cosine of, because you have a 3, 4, 5 triangle there, right?
Yeah, it would be the inverse cosine of.
Not inverse cosine of. Remember like what we did with the 5, 12, 13 triangle? You don't need to do the inverse cosine because you can find the cosine with those numbers, right?
Right.
It's a similar triangle.
Yeah, it would be,
Can you see it? Is it too small? It's too small to print out?
yeah.
It's a 3, 4, 5 triangle.
4 or 5?
Yes. Mm-hmm. Yep. And the y component would be?
It's going to be plus or minus 8 and 16.
Uh-huh.
And
Yes.
5/3?
3 over 5.
3/5, yeah.
Yep. Minus 3/5, about 8/50. Yep. You see that? That's all you got to do. Those 3, 4, 5, 5. Those are actually, they make it easier for you because you don't have to type in a trig thing on your calculator. It's just a fraction. Mandy, do you want to try F2? Yes. Sine 30i. Uh-huh. Uh-huh. 625 cosine 30 j, right? And negative. Actually, isn't the x1 negative too? Yeah, so we got to do that negative. So again, check the signs very carefully. Every time you do a component, make sure you understand it. It's supposed to be positive or it's supposed to be negative. Okay. Duncan, you want to try F3? Good. Sine of 45 because they did the angle to the y-axis. Yep. Okay. And since it's 45, it doesn't really matter because the sine or cosine are the same. But yeah, that's a good way to do it. Pretty clear. And then you add them together. In case you're interested, the resultant, if you want to check on your calculator, should be minus 168 in the x direction, and then minus 521 in the y direction. Newtons, which will give you a magnitude of the square root of 160. I'm sorry, it's not 168, it's 162.8. I have a typo there. So the magnitude would be the square root of the sum of the squares. It's going to be 546. And the angle is the arctangent of 521 over 162.8, which is 72.64 degrees. But again, that's in quadrant 3. So from the positive, sometimes you have to do some, right, so it's in quadrant 3, so you actually have to do 180 plus. So that'll be 253 degrees. Right, because both components are negative, so it's actually, it kind of looks something like this, right? This is our FR. And when you just do the arctangent of those components, it's basically telling you this angle right here. So we've got to add 180 degrees of that to get the correct angle. Question? Yep. Yep. Yes. You could do other additions. Just go and grab the problems from the from the Canvas site, if you can do that. It is? Oh, okay. Oh, all right. Yeah. Well, the thing is, just make sure you do the right problems. And the problems are, did you see where the problems are? Actually, right on here, if you scroll down on this particular lecture, the assignment 1 problems are right here. And you can just pull this up when you're doing the assignment and just do those. Mm-hmm. The text itself, I'm quite positive, is probably identical. So they just changed the problems around a little bit. Yeah.
So for the format, I already started it. I noticed this, like a given time solution.
Yeah.
Is that how you want it? Because I just ended up doing the problems like that.
Yeah, some of them are so simple you don't have to do that. But when they get more complicated, it's a good idea to kind of write the given time.
So should I just go back and maybe?
No, don't worry about it.
Okay.
Just in general. Yeah.
All right.
Yeah, cool.